So a very good morning to all of you. This is the second talk in the ITCU webinar series. And I'm Rohit B, Project Scientist at International Center for Ocean Information Services, Hyderabad. And today I will be talking about a recent discovery made by my colleagues and myself in the Indian Ocean sea level. So, and that is entitled New Rhythms in the Tropical Indian Ocean at Intraseasonal Timescale. The results I will be explaining here are published in Nature Communications, entitled Basin-wide Sea Level Coherency in the Tropical Indian Ocean, driven by Madame Julie Oscillation. And this is the work that made all of us proud by receiving the World Meteorological Organization Award 2020. So first, basically we can start with a small introduction to what is meant by barotropic sea level. For simplicity, we can divide the sea level oscillation into two components: baroclinic and barotropic sea level oscillations. For example, consider an ocean with only 6 to 7 density layers, which can move independently to each other, as seen in these two figures. Here we can have two conditions. In the left, when acted with a wind force, the top two density layers oscillate upward, whereas the rest all the layers moves downward. This oscillation in the density layers creates depth varying horizontal velocities, the blue arrows you can see here. Sorry for that. Okay, so I will, sorry for that. So this is an introduction to barotropic sea level, what it exactly means. For simplicity, we can divide the entire ocean into two components, or sea level into two components: baroclinic and barotropic sea level oscillations. For example, just consider an ocean which with only 7 to 6 density layers, as you can see in these two cases. And these layers can move independently to each other, as seen in these two figures. Here, we can have two conditions. In the left, when acted by a wind force, the top two density layers move upward, whereas the rest of all layers move downward. This oscillation in the density layers creates depth varying horizontal velocities, these blue arrows, eventually creating vertical velocity, the red arrow. The divergence of mass in the bottom layers and convergence of mass in the surface layers causing a net mass to compensate each other. This scenario represents the first baroclinic mode of sea level oscillation, and the sea level associated with such infinite number of density modes are called barotropic sea level. But in the second case, when the wind forcing is strong, when compared to the earlier case, you can see a large wind, the oscillation created by this wind in the ocean causes the entire density layers to tilt upward or downward, causing a convergence or a divergence in the water column. The sea level associated with this oscillation is called barotropic sea level. Here, in this talk, I will be focusing only on the part of sea level that causes the entire water column to oscillate irrespective of the depth. Here is a spatial representation of the earlier findings of barotropic sea level. The previous findings are more biased towards extratropics and polar regions, which includes Arctic Ocean, Southern Ocean, small closed basin like Mediterranean Sea, etc. Other than barotropic variability in the tropical Pacific, there is no evidence of barotropic sea level in the tropical oceans. You can see there is nothing. So we eventually neglect the barotropic variability in the tropics, and we typically assume that the tropics is entirely associated with baroclinic process. But 40 years before, Willebrand, in one of his works in JPO, Journal of Physical Oceanography, talked about the possibility of the generation of depth independent motions in the ocean, that is barotropic motions, forced by atmospheric disturbance larger than 100 kilometers in spatial scale. But the tropical Indian Ocean, even though it has winds of large scale atmospheric disturbance like IOD, monsoons, Madam Julie oscillation, etc., we neglect this barotropic sea level variability. And according to Willebrand's results, these atmospheric disturbances in the Indian Ocean must produce barotropic variability. So, how meaningful is to neglect the non-tidal barotropic variability in the tropical ocean? This is a very big question, which I will be addressing here. But the main problem is how to identify it. It is very hard to distinguish between barotropic variability from the total sea level variability. One way is to look for ocean bottom pressure signals, deep ocean bottom pressure signals, which in theory dominates with barotropic signal. And we identified that there are bottom pressure recorders, in short BPRs, in the global ocean, which is used as a detector for tsunami waves. Here in the schematic is one of the instrument which has a pressure recorder. It's a bottom pressure recorder which is kept at the deeper parts of the ocean, that is more than 2 kilometers. So whenever there is a convergence, so it like a water column, it is a water column and these are the BPRs placed. And when we have a convergence of water at a location which has a sea level change of 4 centimeters, the bottom pressure measures it and it converts the values into an equivalent water depth. You can see it here, water depth, around 4,000 meters of water column, equivalent to 4 kilometers. So the variability is very small. You can see 4 centimeters of variability only it is happening. And these bottom pressure recorders are so accurate that it can measure as small as 1 millimeter variability in sea level. So as a primarily tsunami warning center agency in COIS has also deployed BPRs in the tropical Indian Ocean. There are 3 BPRs that we have, 2 BPRs that we have deployed in the Indian Ocean, one in the Arabian Sea and one in the Bay of Bengal. So it is marked as BP, that is bottom pressure at Arabian Sea and bottom pressure Bay of Bengal. And NOAA also is an tsunami. NOAA also kept this bottom pressure rest of the global ocean. So we have also taken one in the Northwest Australian Basin. This is the BPR sitting here, and one in the Central Pacific. So the data from the VPS are freely available. So these data are available from National Data Buoy Center, NDBC. As I told earlier, these instruments are placed preliminary to detect tsunami waves. So a 2-step quality control processing was done to filter out the high frequency variabilities along with instrumental drift, etc. These instruments are too sensitive. And finally, oceanic tides were removed along with a low pass filter of 200 days. And this is the final time series from these BPRs. We can find that we have barotropic variability at all the 3 locations. So black represents Bay of Bengal, red represents Arabian Sea, and blue represents our Northwest Australian Basin location that is near to Australia. And the values are in equivalent water depth, it is in centimeters. Okay, so almost all the location we have an amplitude. That means we have a variability in the bottom pressure, and it is barotropic in nature. Mostly it is barotropic in nature, and the variability seems to be amplified during the winter months. Specifically, you can see it in 11, 12, 12, 13 and 14, 15. The variabilities are too high. It goes up to 4 to 8 centimeters of variability. But to know more about the frequency associated with this time series, a wavelet spectrum was plotted for these 3 BPRs. This is for Arabian Sea, Bay of Bengal and Northwest Australian Basin. In these 3 plots, the x-axis is in time and y-axis is in period, and the color indicates the energy of the signal. So whenever there is a yellow color that you see it in the picture, it represents that during this specific time and during this specific period, the BPR had a large oscillation, as simple. On an average, the maximum variability in these 3 BPRs is seen during the lines that I have plotted, that is for 30 to 80 days. You can see the energies are maximum. You can see more yellows between these things. And this represents an intraseasonal frequency. And also you can find it has it and its maximum during, it is seen maximum during the winter months, specifically during December to April. So AA means April, April, August and December, these kind of time scales. To know more about the variability, a cross wavelet analysis was carried out. So it's just a cross wavelet analysis between two pairs of BPRs. So I have taken Bay of Bengal as a common BPR, and Arabian Sea Bay of Bengal BPR was cross correlated, and also Bay of Bengal Northwest Australian Basin, that time series was cross correlated. This is quite similar to an earlier plot. These plots are both are similar, but there are arrows. So the color represents the coherency. The yellow color is more coherent, and the arrows represents whether it is in phase or not. And it is surprising to see that even though these BPRs, as I told you, it is located thousands of kilometers apart, one is in Bay of Bengal, one is in Arabian Sea, but during winter times, especially during 2011-12, 12-13 and 14-15, these three BPRs oscillate synchronously. You can see whenever there is an arrow which is pointed towards right, it is in phase oscillation. So this phase is 0. That means both BPRs, both variabilities are happening simultaneously. So these three signatures, you can find it here also during the 11-12, 12-13 and 13-14. And the period that I already told you, it is around 30 to 80 days. So this is also well evident from the, so we can have a frequency analysis, frequency filtering, and a bandpass filter can be done for these time series. So you can find this is well evident from 30 to 80 days filter time series also. So you can find these 3 years are specific, and during December to April we have a synchronous oscillation. And this is the first evidence of a significant barotropic sea level signature in the tropical Indian Ocean. So till now we were neglecting it. We thought it was not it was present, but it is very negligible. It is in millimeters or less than that. But here we have in centimeter variability. And its more exciting part is that all the three BPRs are oscillating synchronously with an amplitude of 4 to 8 centimeters during December to April at 30 to 80 day period. So from here onwards, we will restrict our analysis only for December to April and for intraseasonal time scale. The synchronous oscillation in these long distance BPR signifies a possibility of a basin-wide barotropic oscillation. It's kind of a basin-wide, it cannot be a local process. To check this possibility, an equivalent water depth from a satellite known as GRACE was used. A correlation was carried out between one of the BPR in the Bay of Bengal and the GRACE satellite at intraseasonal time scale during only December to April. And here evolved the basin-wide structure of the barotropic sea level variability observed by these BPRs. It covers the entire tropical Indian Ocean. This means during December to April at intraseasonal time scale, the entire tropical Indian Ocean goes up and down synchronously. And this is spatially one of the largest sea level variability ever observed in the global ocean. So you can see the entire Indian Ocean is a positive correlated. So the entire Indian Ocean goes up and down, and our three BPRs were located in this pattern. And the important question, or the immediate question which comes to our mind, that what forces this oscillation and what is the dynamics behind this? One of the possible candidates here can be atmospheric forcing, wind or pressure. And according to literatures, wind forcing is most prominent candidate than surface pressure. But wind forcing can have local and remote origins basically. Incorporating assumptions like incompressibility, inviscid, linear, homogeneous, there is no atmospheric loading, these kind of things, we can write the wind forced barotropic vorticity equation as this down equation. And this eta represents the barotropic sea level. And the left hand side is the effect and right hand side is the forcing term. Forcing and tau is represents the wind. So del cross tau by h is the forcing for a barotropic sea level variability. So to identify the wind source, we correlated that same BPR that we used for the GRACE correlation the Bay of Bengal BPR, which was correlated with the source term of our wind barotropic vorticity equation, del cross tau by h. The data was taken from NCMRWF winds, and this was the correlation pattern. The correlation was only significant in the eastern Indian Ocean, a small box near to Northwest Australian Basin, one of the BPR that we have here. So when we correlated Bay of Bengal BPR, we thought we have a correlation near to this source, but we have entirely an area where we didn't expected it. So, but this area is important in any of the intraseasonal process, because we have an intraseasonal variability, isn't it? So whether it is important or not, the intraseasonal variability in the barotropic seal made us think that the wind forcing can be by Madame Julie oscillation, one of the strong or one of the intense tropical wind forcing or wind event that circles the entire global ocean. The field pattern here in this animation, so this is a schematic, not a schematic, it is a composite of picture of MGO cycle, and the field pattern corresponds to precipitation, and associated with this precipitation we have wind also, and the moving blue patch corresponds to a heavy rain and low pressure area, and the red patch associated with a high pressure area, and the movement of this low pressure or high pressure and its associated wind from the western Indian Ocean through Pacific circling back to this Indian Ocean is called one MGO cycle, and the movement is corresponds to it is divided into 1 to 8 phases. So first phase is an patch where the low pressure sits in the western Indian Ocean, and 2 central Indian Ocean, and it goes like that, and 8 coming back again to the African continent. And this is how MGO patch looked like. The movement is described as numbers, as I told, 1 to 8, called the phases of MGO, and the magnitude also represent in by magnitude of the MGO, because how much the OLR or outgoing long radiation or the wind forcing it is. From literatures we identified that, so this is from a literature we can identify that the color in this figure represents the magnitude or the amplitude of the Madame Julie oscillation, and the contours represents the wind forcing. So there are 3 major MGO forcing patches in the global ocean, one in the central Indian Ocean, one above our above our Northwest Australian Basin, where we saw our correlation was maximum, where the intensity of MGO and the magnitude is large, and another one is in central Indian Ocean. So for better clarity, so there is a clue that Madame Julie oscillation winds or the pressure associated with it crosses the Northwest Australian Basin or our area where we got our correlation. So this is a clue, but how to properly identify? So this is a composite, as I told you. This is one of the this is another composite clubbing all the 60 plus 60 boreal winter. Boreal winter means winter MGO events, and this plot was adapted from Billiger and Duell 2012. So to know for better clarity of the MGO forcing, we compared an year by year variability of our barotropic sea level. So this is a time series from 2011 to 2015, and only December to April. This is the observation taken from Bay of Bengal location, the top panel, and the bottom panel is the MGO index. So MGO index means we have the colors and the steps. So the colors represents the magnitude of MGO. That means if it is red, it is larger, the powerful MGOs, and the steps represents the 1 phases. So it starts from 1 and it ends in 8. As I told you, it is a oscillation from Western Indian Ocean throughout the Pacific, coming back to same. So one step represents an MGO propagation. So and x-axis is in time. The shaded cyan color in the index represents the Madame Julie oscillation location around Northwest Australian Basin region. From this plot, it is evident that during 11-12, 12-13 and 14-15, we observe a strong barotropic sea level variability. This is accompanied by a strong Madame-Julie oscillation passing along this region also. So it is concurrent. It is similar with our magnitude. If we have a larger magnitude in the barotropic sea level, associated with that, we also have a Madame-Julie oscillation passing along the region. So the Madame-Julie oscillation winds hovering over the northwest Australian basin can be a source for this observed variability. From this finding, it is evident that, but it is not conclusive. We want to use a general circulation model and try to reproduce the observed barotropic sea level variability by forcing winds only in the northwest Australian basin. That conclusively we can say that winds in that region is important in forcing this. So before that, we want to have an ocean general circulation model, and for this purpose, here we use modular ocean model, which has a semi-global domain. First, we will try to reproduce the barotropic sea level variability seen in the Bay of Bengal, BPR in the Bay of Bengal location. So for that, we force the model globally with all the atmospheric fluxes. The dotted line is the time series of the barotropic sea level extracted from the Bay of Bengal location, the gray shaded one. The dotted one. The results were convincing the model could reproduce the observed barotropic sea level variability, that is at least seen in the Bay of Bengal location, which has a reasonable accuracy also. You can see even though it is overestimating sometimes, this is specifically during 11, 12, 13, but the pattern, it got the pattern. So this gives us a confidence to try for some experiments using this model. So next, we ran the model by forcing winds in the northwest Australian basin. You can see in left. So we forced winds only in this box. We made the rest everything 0, and we compared. The time series were extracted from the Bay of Bengal. Just for a comparison, we are taking only our Bay of Bengal as a representative of all the BPRs or the global Indian barotropic sea level variability. So just a Bay of Bengal location as a reference. And the green line represents the barotropic sea level extracted from our run, that is forcing winds only in the northwest Australian basin. The model reproduced almost 60% of the observed barotropic sea level variability, confirming that northwest Australian basin is that region, the box region, is most prominent forcing region for the observed barotropic sea level variability. Specifically during 11, 12, 12, 13 and 14, 15, the northwest Australian basin forced model was able to mimic the global forced simulation. Almost it is getting it. They were confirming that the winds hovering or winds forcing over the northwest Australian basin are causing the entire Indian Ocean to oscillate. So we could get a most prominent forcing region for this variability. As you know that variability, the variability that I am talking about is barotropic, the total barotropic. So even with a barotropic model, we must be able to reproduce this variability. So for this, we ran the model, the same MOM model, by making the system homogeneous. That means non-stratification. We took out the temperature and salinity inside this model to make that constant. So make this homogeneous. So the three-dimensional temperature and salinity was relaxed to kind of constant value 15 and 35. That made our model barotropic, almost barotropic. And we ran the same experiment by forcing winds over the northwest Australian basin. That is the cyan curve. The green curve is the stratified, that means our normal experiment, and the cyan curve is this with the non-stratification experiment. The model could only reproduce the observed variability by 30% when compared with the northwest Australian basin experiment. And this confirms that stratification plays a main role in modulating the barotropic variability. It is quite counterintuitive for a classical barotropic dynamics. it was very surprising for me to run this experiment, seeing that stratification needed for barotropic. And similarly, we also run another experiment by reimposing stratification. We reimposed stratification, but we took out the bathymetry. That means we made the made bathymetry to be deep bathymetry to be constant. We put 3000 meters as the bathymetry throughout the Indian So that is 3000 meters in the average depth of the Indian So we made that, and we ran the winds, or we ran the model by forcing winds only in the Northwest Australian Basin, this box region. And here also we had an underestimation of barotropic variability of about 30% when compared to the Northwest Australian Basin experiment. This pink and the green curve, this is underestimating. The pink was underestimating. So as a conclusion, stratification and bathymetry of Northwest Australian Basin region are quite equally important in reproducing the observed barotropic variability. So now we know that the forcing region. So the Northwest Australian Basin is the forcing region for this variability. But the next question, exciting question, will be what is the dynamics that causes the entire Indian Ocean to oscillate synchronously? So sorry for that, the animation is not working properly, but we made an animation using 1 hour model outputs from the Northwest Australian Basin forcing experiment. So you can find here we are forcing the winds, and this is a time series. And if you want to have a this animation, you can scan this QR code. You will get this animation in your mobile or thing. So it's a cool animation. And the right side is the set of winds that we are forcing. The model is seeing. So here we are forcing the winds in this box. This is the wind is taken from NCMRWF, and here is the sea level output, and the lines represent the F by H contour. And these lines are quite important because we are seeing this variability is restricted, or it is kind of this F by H acts as a wall by blocking the entire variability spilling over to this basin. So to know more about this waves or this dynamics, what we did was we made many experiments, sensitivity experiments basically. One of the experiments was making the Coriolis parameter to be constant. So we made our Earth to rotate constantly, not latitude varying. And also we made flattening bathymetry over the Northwest Australian Basin. And also we flattened our 90 east ridge, that is a ridge that is here, whether this ridge is important or not to see. And also another experiment, we cancelled or we removed the southeast Indian ridge. This is another ridge that crosses. So we made these kind of experiments, and we identified that there are 3 types of waves which is generated from our forcing region. This is our forcing region, and 3 waves are generated. One is called a planetary Rossby wave, which has a speed of around 50 meters per second, which propagates from this our forcing region towards North Indian Ocean. And this Northwest 90 east ridge also diverts or guides this wave towards north. So this ridge is also important. Without this ridge, it will not go towards north. One of which has a speed of around 50 meters per second. That is within a day, exactly 23 or 25 hours, a wave which generates from this region reaches our Arabian Sea. And even though this wave has a delay, this within a day it reaches. So we are not seeing a delay in these 3 bottom pressure recorders. But if you go towards higher resolution time period, we may see a delay in the barotropic sea level variability. And another wave, the second wave, is called topographic Rossby wave, that propagates along the South Australia and curves around this F by H contour, the contour that passes through the southeastern Indian ridge and flows towards south. And this is called topographic. Why? Because it requires topography. When you remove the topography, this wave is not present. So it wants topography. and it has a small, I mean it has a very less speed compared with the top Rossby wave, which has 17 meter, which is having a speed of around 17 meter per second. So these are the two waves which existed in this ocean, and it is generated from the Northwest Australian Basin. And these are the two waves which causes the entire Indian Ocean to oscillate, which is too fast, so it fills the entire Indian Ocean. And the ridges that I already told you, 90 East Ridge and Southeast East Indian Ridge, is very much important, which basically blocks this variability to reach the Southern Ocean. If this ridge was not there, it spills out to the Southern Ocean, and the sea level rise that is happening as 6 to 7 centimeters will not be there. It will be very small. So with the help of fast moving waves and the existence of ridges, that is 90 East and Southeast Indian Ridge, the wind forcing over the Northwest Australian Basin causes the entire Indian Ocean to oscillate synchronously. So this animation that if you want to see, please scan this QR code. You will get a proper understanding of how this propagation looks like. So right now we know that so Indian Ocean is rising. Indian Ocean is rising in 30 to 80 days, and draining off also, and also which is forced by the winds of Madame Julie oscillation. And there is a specific region where this Madame Julie oscillation is forcing this ocean. This is called Northwest Australian Basin. It is a basin, and this wind causes fast moving barotropic waves to propagate, and this causes this fast moving barotropic waves, which causes a synchronous oscillation in the entire Indian Ocean. So as a summary, the fast moving barotropic waves is a reason, and also it gets the help from ridges in the Indian Ocean, cause the entire Indian Ocean to oscillate synchronously. But for the basin-wide synchronous oscillation, Indian Ocean requires water from somewhere, isn't it? Because it is rising 4 to 6 centimeters, the entire Indian Ocean is going up, and it is going down in 30 to 80 days. So there must be a source or sink for this variability. To identify this, a correlation was done between the model barotropic sea level from this source region and barotropic sea level throughout the global ocean, and this was taken from our Northwest Australian Basin experiment. It was very surprising that a positive correlation is seen for the entire Indian Ocean that we have already seen from the satellite gravity measurements or the satellite data. But there is an anti-correlation, or the out of phase correlation in the Pacific Ocean is being evidently seen. Tells us that Pacific Ocean might act as a reservoir for this Indian Ocean barotropic variability. It looks like during a sea level rise in the Indian Ocean, that means if sea level is raised in the Indian Ocean by forcing the winds, the water from Pacific Ocean drains or fills into the Indian Ocean, causing a sea level low or high in the Pacific Ocean. So whenever Indian Ocean rises, Pacific Ocean drops, and the water is taken from the entire Pacific Ocean. Is it really happening, or this is small an artifact? So this was identified, or this was validated from a BPR which sits in the Pacific Ocean. So we compared one of the BPR, that is the Bay of Bengal BPR, and another BPR from the Pacific Ocean. So this is a time series of these two BPRs from 2011 and to 2014, only during December to April. And you can see the green color is the BPR from the Pacific. Whenever there is a strong signal that seen in the Indian Ocean, specifically around 11, 12, 12, 13, you can see these things. The Pacific Ocean BPR, or the sea level in the Pacific Ocean, goes down. That means whenever there is a raise in the sea level, Pacific Ocean goes down, as seen in this correlation, similar to the correlation that we are seeing. So, is there an Indo-Pacific seesaw? That means there is a seesaw happening in the Indian Ocean in the intraseasonal time scale. If it is, then there is a large scale Indo-Pacific mass redistribution is happening. Redistribution means the mass of water is coming from Pacific Ocean to Indian Ocean when Indian Ocean wants water, and the other way happens. Indian Ocean drains water to the Pacific Ocean, causing the other oscillation to happen. So we are right now working on it, and we find that this is really happening in the global ocean. So what are the implications? So you can find there are a lot of large scale mass redistribution, these kind of oscillation, the entire Indian Ocean is in the Indian Ocean is happening. So what are the implications? The most important one will be the reduction of adjustment time scale of MGOs. In Indian Ocean, we have, in the literature, it is seen that if Madam Julie oscillation winds or the sea level related to Madam Julie oscillation has a delay time of few weeks, basically few weeks or months. But because of this variability, within a few hours, the Madam Julie oscillations sea level variability reaches the entire Indian Ocean region. So there is a reduction in the adjustment time scale of the MGO. And during each barotropic sea level cycle, that is 30 to 80 days, the barotropic flow model derived velocities, basically the flow associated with this, is estimated to be 1 centimeter per second. So that means the entire Indian Ocean or the entire total water column moves 1 centimeter per second. So does the sea level, the level of motion exist? Does the level of motion exist in the ocean? So this variability can alias into the low period variability too. So we were neglecting, as I told you, we were neglecting these kind of variabilities. So we were neglecting. So this variability can alias in the low period variability, causing an error in the sea level rise estimate also. So to while understanding or while calculating sea level rise, we want to be sure that this variability is not there. And even though a barotropic model, as we already shown that barotropic model is not sufficient enough to explain or to explore, to explain this full variability, a coastal inundation forecast, during a coastal inundation forecast, during a cyclone scenario, if the error associated, if a variability or a MGO happens, there is an error associated with it in the coastal, and this can cause errors in the estimate of inundation also. And also while using an altimeter like Aviso, and we think that in the Indian Ocean or tropical basins, the data from altimeter is purely baroclinic in nature. But now you know that it also has a barotropic signature. So before analyzing barotropic sea level variabilities kind of thing from Aviso data, we want to remove this barotropic signal completely. Otherwise, there is an error associated with it. So this signal must be considered while closing the budget of the sea level. Budget also, using sea level budget, calculating this variability also must be considered. And the signal must be considered while and finally this barotropic sea level variability can also influence the interbasin transports. As I told you, there is a large scale redistribution happening in the ocean. So during the redistribution, there can be large transport associated with it. Specifically in the Indonesian true flow, where there are small straits, there can be large transport associated with it. So while understanding the transport from Pacific to Indian and Indian to Pacific, you want to have an idea about whether there is a barotropic sea level variability happening in these gradients or not. So as a summary, a takeaway message will be, during December to April, the Madam Julie oscillation winds hovering over Northwest Australian Basin radiate intraseasonal barotropic waves of amplitude 4 to 6 centimeters that invade the entire North Indian Ocean, causing a basin-wide oscillation. Thank you for that listening. And this was a short presentation, short webinar basically. This was my work. Now you can ask questions in the chat box. So possibly I will be answering most of the questions if you have any queries. So as I told you, this work was published in Nature Communications in the title Basin-wide Sea Level Coherency in the Tropical Indian Ocean, driven by Madam Julie oscillations. So this is a schematic which I was created by to understand how globally this is important. So you can find the waves associated with it and the area where Indian Ocean is rising. Thank you. So you can ask questions in the chat box regarding the topic. So there is a question that I would like to know where there are any variability in the data collected by GRACE satellite when it passes over Indian and Pacific Ocean. Variations in the data. So the the GRACE data, the GRACE is a satellite basically. It measures gravity. So as a simple example here, so there is a two satellites paired. It is not connected, but it is separated, and it measures the gravitational pull. Gravitational pull. It measures the gravitational pull, and in related to that, it measures sea level variability, or the mass associated with it. So while this data is freely available, so I have used a 10-day product from GRACE, and it gives the equivalent water depth. That is, it converts this mass variability into sea level, and this variability, and I am finding the way. I am finding this variability in the Indian Ocean, and also that seesaw that I told you, it is also seen in the Pacific too. But in this paper, I have not talked about the Pacific role or whether it is really happening in the Pacific or not. But in the Indian Ocean, GRACE measures, or GRACE gives a synchronous oscillation. That means we have a synchronous oscillation from the observations. So how these recent findings will impact Indian Ocean dipole formation and dissipation, if it does? So right now, as I told you, this is kind of a barotropic variability. So basically, I have taken out the thermal part. That means I have not incorporated the thermal variability. So as you all know that sea level can be changed by thermal variability, and the surface of the ocean is connected with the atmosphere. So there are variabilities which generates as Indian Ocean dipole, these kind of things from this region where it is near to Northwest Austral Basin, and the NGO is having a pass through that region also. But we are not pure sure about how it imparts to the thermal part of the ocean, because right now I have fully talked about the dynamical part, but I don't know exactly how it imparts, but we think that these waves generated from this northwest Australian basin, that means the fast moving barotropic waves, hits into the ridges part. As I told, ridges are interacted, the waves interacts with the ridges, causing dissipation. We are planning to work on it to know how this energy is dissipated into the ocean. Maybe in future we will have some understanding of how it imparts to the other processes. So right now we don't know more about this energy dissipation of these waves, which creates some variability in the thermal part of the ocean. So dissipation, there will be dissipation, 100% sure, but we are not sure about right now how and why. How do you get the MGO index data? So the MGO index data is a that is also freely available in the websites that our Australian agency are getting. So this is kind of a second empirical orthogonal functions modes, first and second. So it can be. So I will just I will give you a link where you can download the data. It is RMM1 and RMM2 indices, first and second mode of this EOF. That can be used, and that they will give us as a phase and amplitude from as you can see here, from the phase and amplitude I have it. From phase and amplitude you can plot whatever type of plots you want. So it is maybe when you see the literatures you will see circles diagram in this like a circle. It is quite complicated. So I think this step diagram is quite simple to know. So as MGO, so next question, as MGO moves forward in the eastward direction, so is the mass movement and sea level variability observed in the Pacific, or is it both the Pacific and Indian Ocean? Okay, so basically as I told you, the only forcing region that till now we have found is this region, Northwest Australian Basin region. So only when MGO, so I will take a larger picture. So you can see a simple diagram like this MGO. So MGO is propagating. So when it moves towards this box, then only this variability is forced. Other than that, it is not. So when wind of MGO comes to this box, waves are created. These waves requires water. So at that time it takes water from Pacific. So this is because this region is kind of a bowl shaped region. Bowl means kind of exactly a bowl. So dynamically speaking, a large convergence or divergence happens in this area, and here also the MGO winds are strong. As you can see, MGO winds are strong here than the other places, and winds are strong, and also the MGOs are intense. So these two factors, and also this specifically this region is important. No other region is quite important, because this region winds only this region is region has 60% of the variability. So 60% of variability comes from this region. So that is the most important region. How does the Rossby wave propagates in Arabian Sea of Bay of Bengal? So basically this is the waves are barotropic in nature. As I told, these waves are barotropic in nature. So these waves creates, so this red line is our Rossby waves. So because these waves are barotropic in nature, this has a Rossby radius of deformation of 2000 plus kilometers. So, and it cannot be a pure planetary Rossby wave because there are topographies also. So but this is a planetary dominated Rossby wave. Why? Because when we did a correlation Coriolis parameter constant experiment, this wave was not present. So this wave requires a beta plane. So this is how we identified that the red color wave is a barotropic Rossby wave, and it generates from this region and it reaches up to here. Then the topography can be overcome, and topography will kick up, and this passes this travels through the ridges towards the Arabian Sea. So this generation of this wave requires a planetary origin. That is sure. So our next question: where can I get temperature and salinity data to calculate steric from 1993 to 2000? So this is a different question. So steric sea level, you can get it from Argo data. That is 1993. I don't know. From 2000, it is quite freely available. You can use Argos and Grider Argo data from INCOI's website or something to calculate steric sea level calculation. Next question: is it over Indian Ocean, MGO is mostly active when the RMM is in phase 2 and 3? Then instead of taking December to April time, can we go for the time when the RMM phase is within 2 to 5? Exactly. So that is a good question, because when I was just checking the phases, you can see there is a shaded region in the Madam Julie Oscillation Index. So during we are finding that during 3 to 6 phases only this is active. That means during the 3 to 6 phases, between these 3 to 6 phases, our MGO's winds are between Northwest Austral Basin. So you can take both as a criteria. So I have taken December to April because it was very tough to take 3 to 6 as a phase or 3 to 6 as our MGO's propagate or barotropic signal phase or the time period of our variability. Why? Because this doesn't have a seasonal variability. That means during December to April, the MGO that one more second. So during December to April, the MGO passes through the southern part of the ocean. During the summer times, it passes towards north. So even though there is a propagation, but during the winter time only, the MGO is mostly seen in the Northwest Austral Basin, or its peak or the center part comes into the Northwest Austral Basin. The other months, this passes through near to the Northwest Austral Basin. So this information of seasonal variability in the MGO pathway is not there in the index. So that's why I didn't took the index as the reference. But during the December to April, we are almost sure that the MGO propagation comes towards Southern Ocean or near to the southern part of the ocean and over to the Northwest Austral Basin. So that the other question that both can be taken. So can you explain how another question, can you explain how the bottom pressure recorder works? What is the measurement transmitted? How long does this? Okay. So this is the bottom pressure recorder. So this bottom pressure recorder is, as I told, basically kept for the tsunami detection thing. So there are two parts in the bottom pressure recorder. One is a bottom pressure gauge which sits in the ocean, and another one is a buoy, and this measures the bottom pressure. It's simply a pressure recorder. So it measures the pressure of the water plus the atmosphere, the total pressure imparted by the ocean and the atmosphere. And it, for a normal mode, that means there are two modes for this pressure recorder. One mode is called it is a normal mode, and another one is the active mode or the tsunami mode, where in a normal mode it measures or it transmits data every 15 minutes. So every 15 minutes we have one value, and I think it is 15 seconds it measures it, and it averages, and it collects and it transmits. They transmitted acoustically to the surface buoy, and the surface buoy transmits it through satellite to our tsunami warning center. In an active, so in a tsunami mode, it measures for minute wise or even second wise, maybe 30-second wise for measuring the tsunami wave properly. So these are the pressure recorder, a minimum understanding of. I don't know much about the technical details of this pressure recorder, but this is how it measures. So another question, any future studies plan to know exactly what part of the Pacific Ocean is responsible as source for the sea level variability mentioned? So I mean, yeah, exactly. So I have mentioned that this variability that we are finding in the Pacific Ocean, that I will go to that figure, then many people will be rating. So this variability that I am finding in the Pacific Ocean is purely related to Indian Ocean, mostly, because whenever Indian Ocean requires water, Pacific Ocean gains, or from Pacific Ocean it takes. There is no other most sources. There can be sources because Pacific Ocean is too large, and there are other wind sources here also, but as a maybe 20 to 30 percentage of this specific variability in sea level corresponds to Indian Ocean variability. That means Indian Oceans is the source, and Pacific is a reservoir. So I think Indian Ocean, Pacific is a slave for Indian Ocean variability, as simple as that. So I think there is a seesaw, Indo-Pacific seesaw existing in the Indian Ocean, and we have already, analyzed it, and we have wrote a paper on that. It is communicated basically, and most probably it will be accepted, and we will have a understanding of how this happens and what are the large-scale implications of this, one of the largest, globally the largest sea level oscillation ever observed, basically. So next questions. So from the previous answer of phase, things can say that whenever the coherency you are talking in is applicable only during December to April, because during summer the forcing will not be within this box. Exactly. So, but I cannot say specifically that the forcing will not be there. The MGOs will be passing near to equator, or little bit above. So there can be winds associated with this pattern during summer times, but not properly. So the MGO pattern is not small, as you know. It is a large scale pattern. During these winter months, the pattern will be purely over the Northwest Australian Basin. So a large winds can be seen in this Northwest Australian Basin, but during summers, a part of it. So when you see my time series, the total time series that when I was not restricted, example, I will just take one or two examples. So exactly here. So you can see during a 2011 August September, there is a small synchronous variability, but it is not as large as December to April. So during maybe this time, there was an MGO which passes across equator, and it's a small pattern, or the winds associated with it might reach to the Northwest Australian Basin, but that is not powerful. Similarly, you can find some variabilities in the April or September months where there are MGO times. So I would say that mostly a large significant barotropic sea level variability is observed during December to April. So that is quite important, because you can find 4 to 6 centimeters of intraseasonal variability, or 3 to 8 centimeters of intraseasonal variability. It's quite large, because the intraseasonal variability, total intraseasonal variability that we are observing is around 10 to 12 centimeters, or it is around 10 to 12 centimeters from AVISO altimeter data. In that, around 60% is seen during this time. So it is quite large. Any connection with the southern oscillation? Yes. So recently we are finding some connection, because MGO has a connection to the intraseasonal southern oscillation. El Nino southern oscillation. No, I'm not finding it directly direct link, but the southern annual mode has a connection, because MGO directly imparts to the currents in the Southern Ocean, intraseasonal currents in the current variabilities in the Southern Ocean. So it has a direct contact to the Southern Ocean currents. but I don't know about El Nino sea level variability and these kind of variability because we don't have much data. This BPRs was deployed in the Indian Ocean from 2010 onwards, and there are huge problems in the not problems, huge drifts, because these are deployed in the center oceans or the deeper oceans, so it is very hard to process it. So processing takes a lot of time to get proper the signals out of it. So, and as I told you, I have band passed or low passed it to 100 days. It is because large scale or small scale low frequency variabilities are very confusing, whether this bottom pressure is sitting in the mud or the sand in the ocean. So it also varies. The weight of this bottom pressure alters the sea level because it goes down or up according to the mud, which is, or the condition of sand it is sitting. So I think right now we are not able to, or we cannot have a decadal or 5-year periodic variability extracting from these BPRs. Less than seasonal or less than annual is good enough, I think so. So I don't know the impact in the southern oscillation in these things. So any more questions? So thank you very much for your attention. For any queries regarding this, so please mail me. I will give you the details regarding this, and please go to my, if you want to have more knowledge, more things, more understanding about this recent paper that our colleagues and myself written, please go to the Basin-wide sea level coherency in the tropical Indian Ocean driven by Madam Julie oscillation. It's a very quite interesting paper that we have find out. Thank you very much.